dark matter, in particular for light dark matter, and I will define in a moment what light dark matter it is for us. And so I will try to give you an overview of what are the main searches in this field, and starting from searches at colliders, where I will focus a bit on the LHCb searches in the dark photon decays. And then I move to fixed thin target, and then to beam dumps, and finally to missing energy or missing momentum experiment in the last day. But first of all, I will have to introduce very fast the model that I'm going to consider throughout all my lectures, because as Javier said in the talk just before, in order to talk about dark matter in accelerator experiment, we have first of all to define the models we are addressing, because otherwise it's not easy to link our phenomenology at the accelerator to what dark matter may be. So, next. Okay, first slide is stolen, so I took this slide from the lessons you had last week from Graciela Gelmini, showing what are the main astrophysical proofs and evidences of dark matter that we have right now. So you have these many observations, such as the rotation curves of galaxies, anisotropies in the cosmic microwave background, structure on a large scale, all the measurement from gravitational lensing, and the very striking proof coming from the bullet cluster. So this is just to say that, as you for sure now know better than me, that all the evidences that we have from dark matter comes from astrophysical observation, and so from the gravitational interaction of dark matter with our world. This is very known, but this is translating the fact that we have no information on what is the particle nature of dark matter. We don't even know if it is actually made of particles. Next. So in fact, if we rely only on the astrophysical observation to constrain what may be the mass of a particle dark matter, we see that this window is incredibly large. We go from 10 to the minus 20 electron volt up to 100 solar masses. So from almost massless particle up to primordial black holes or astrophysical scale object. So it's obvious that if you want to build an experiment searching for such particle or such entity, we need to close this window a bit and somehow define a strategy to search for some particle in a limited mass range. For example, if I want to search for a particle with mass order 1 TeV, I will build such an accelerator with such an energy. If it is 1 GeV, it will be different, and it will be, if it is solar mass, I will probably will change job. So this is the reason why we need theoretical guidance to close this window and define some targets to search for. And next. This guidance may come from cosmological hypotheses. So you already saw this picture here, which is the picture that defines what is the achieving of a dark matter density in the universe through a freeze-out mechanism. So this very popular hypothesis, called the thermal dark matter hypothesis, assumes that dark matter is made of particles, and that at some point in the evolution of the universe, due to the high density and high temperature in the primordial universe, dark matter was in thermal equilibrium with standard model particles. This equilibrium was achieved through an annihilation reaction, where you have two dark matter particles called chi going to standard model particle. And this reaction could be achieved in both directions. So in the first phase, that I cannot point at, but it's the first part of the plot, basically the number of dark matter particle in the universe is stable. Then, as the universe cools down, the temperatures is such that the average energy of the dark matter particles and the standard model particle goes below the mass of the dark matter candidate, and then the reaction of annihilation cannot go anymore into the two directions. So it will be limited from the dark matter world to the... Oh, thank you very much. Okay. It's working? Yeah, it's working. So I was saying the reaction is limited from the dark matter world to the standard model. That is the Boltzmann regime, where you have when you have the dark matter density and number of dark matter number particle decreasing exponentially. And then, as the universe expands and cools down up to a certain level, where the dark matter particles cannot no longer find each other, they stop annihilating into the standard model. They are decoupled, so this is the freeze out, and the number of dark matter particles in the universe remain constant. So this is the so-called freeze out mechanism, and it's quite obvious that by observing how much dark matter is there in the universe now, we can put constraint on the dark matter nature. In particular, In particular, it's intuitive that if the annihilation cross-section of dark matter into standard model particle increases, the freeze out will be reached later in time, and therefore at a moment where the dark matter density in the universe is lower. So really we have a way, considering this theory, to bind the Rayleigh abundance to the annihilation cross-section and to the mass of a dark matter candidate we are considering. So I won't go into detail here because you already heard it, the lectures last week. But if you consider a mass of order 1 GeV, which is a typical electroweak mass scale, you get that the cross-section of an annihilation is the typical cross-section of electroweak interaction. So this is the so-called Wien miracle, and this basically could allow to explain dark matter introducing only one new particles and no new force. And this was one of the reasons why this model was really attractive for the physicists, because it's very simple. Also, from the particle physics point of view, there were some very popular extension of the standard model, such as supersymmetry, which already included this kind of particles, such as neutralinos, and therefore this seems really a good thing that we could basically include a new particle for supersymmetry, which was also a WIMP, and explain dark matter. So explaining many things with just a new particle. So we have a candidate, we search for it, we find it, where we are done. Unfortunately, that is not the case up today, because there have been many searches in the field of dark matter, in particular in the field of WIMPs, weakly interacting massive particles. And here you have a plot showing the performance searches up to date. So here this plot is on the x-axis, you have the mass of the dark matter particles, and on the y, the dark matter nucleon cross-section. And you can see that we already explored an important part of this parameter space, even if there is still much more room to explore. And experiments which are shown here are so-called direct search experiment, which is a topic of the Javier lectures. And these in general are, just to simplify a bit, large volumes active materials, and where you wait for a dark matter particle to impinge, and then you measure the energy of recoil of the nucleon where the dark matter particle has impinged. So we have searched a lot, we still will have to search, but for now, no WIMP clear signature. So what we can do? we may think if it's possible to search for dark matter with masses lower than 1 GeV. For example, going to the MeV scale. This is motivated by the fact that, as Javier already told, the sensitivity of this experiment, as you go down with masses, decreases a lot. This is due, as he said, to kinematic reasons. But for this reason, these experiments are have low sensitivity at lower energy scales. So the first thing that you may think to do is, okay, let's think of a WIMP which has a lower mass than 1 GeV, for example. Is this possible? Is this consistent with the thermal origin, with the freeze-out mechanism? The answer is no, because as we saw, the cross-section and the mass of the dark matter particles are bound in the thermal origin hypothesis of dark matter with the freeze-out hypothesis. And therefore, if you think of a WIMP which has a mass lower than 1 GeV, so a particle that annihilates into standard model via the mediation of a W or Z boson, the cross-section is such that if the mass is 1 GeV, you will not achieve the relic cross-section which is in agreement with the thermal origin of the universe. So in principle, you cannot think of a WIMP which is a mass lower by 1 GeV, unless you work around the models, but let's keep it simple. So in the simplest way, you can to think of the light dark matter particles, you can introduce a new interaction. So something that makes you achieve the right cross-section to be in agreement with the thermal origins of the dark matter, with lighter masses than 1 GeV. There are many possibilities to think of these new interactions, which are called usually also portals to dark matter. For these lectures, we will stick with one of the simplest, which is also very representative from an experimental point of view. And this is the so-called vector-mediated light dark matter, or dark photon. So the model is very simple. We have dark matter particles that are charged under a new mediator, which is called dark photon, which is a vector boson with mass, so it's massive. And the portal between the standard model and the dark matter sector, it's realized by the fact that the dark photon is kinetically mixed with the standard model photon. So basically, it's like the standard model photon can oscillate with in a dark photon. So here, this model, as you can see, is slightly more complicated than the WIMP's one, because you have not anymore only one particle introduced, so basically 1 degree of freedom, which is the mass of this particle, but you have 4, because you have a dark matter candidate, so the dark matter itself with its mass, a mediator, which is the dark photon, which has its own mass, and then 2 parameters, alpha dark, which in analogy to the electromagnetic alpha of the standard model define the strength of the interaction between the dark photon and the chi particles of dark matter, and the intensity of the kinetic mixing, which defines the strength of the coupling between the photon and the dark photon, which is defined by this value epsilon. Of course, epsilon here has to be small, because otherwise we would already have discovered this particle, because now we are talking of masses in the ranges from 1 MeV to 1 GeV, which are masses that have been already achieved many years ago at Accelerator and the Collider experiment. So if we did not discover this particle, it's because they were feebly coupling to our world. So epsilon has to be much lower than 1. And what about the freeze-out? In this model, we can define a window of a parameter space where the parameters are compatible with the thermal freeze-out hypothesis for the origin of dark matter. So As I said, the model is a bit more complicated. You have these 4 parameters. So what is usually done to also present the parameter space and present the sensitivity of the experiment in this scenario is to build a new variable, which is called y, which is red formula here, which is proportional to the annihilation cross-section in this model. So if you define y, you have that the cross-section is proportional to this new variable y divided by the mass of a dark matter particle to the second. So as a result, for any given value of the mass of a dark matter, you have a fixed value of y, which from an experimental point of view basically tells you what region of a parameter space you have to explore with the experiment to probe this dark matter model in the hypothesis that this is dark matter and this is produced thermally from a freeze-out mechanism in the early universe. As I said, the model is a bit more complicated and it has more free parameters, and therefore it gives rise to a phenomenology which is quite rich. And in particular, if you think to the ratio of the masses of the mediator, the dark photon. The blob. Okay, so this is just a symbol representing the mixing between the dark photon and the standard model photon. This is an effective way to depict this process. Actually, how it is realized is supposed to happen via loop mechanism where very high-scale mass particles participate in the interaction between the photon and the dark photon. But from an effective point of view, for us it's just a blob where a dark photon can oscillate into a photon and vice versa. So this is underline the fact that there is some physics behind, so some higher scale particles probably giving rise to this coupling via loop mechanisms. Okay, so I was saying that depending on the ratio between the mass of the dark matter and the mass of the mediator, you have different scenarios, and in particular, you have different decay possibilities for the dark photon if produced on shell. So, for example, if the dark photon is produced on shell and its mass is larger than 2 times the mass of a dark matter particle, chi, then it will decay mainly to dark matter particle. This is due to the fact that the coupling of a dark photon itself to the dark matter does not have to be small, because we don't know nothing about the dark sector, and we assume it to be a reasonable number as in the standard model QED. Otherwise, if the mass of the dark photon is not larger than twice the mass of the chi particles, dark photon cannot decay anymore into dark matter particles. It has to decay to standard model leptons. And this is the so-called visible scenario, because we can see the products of the dark photon decays. And finally, we have this scenario here, where the mass of the dark photon is lower than 1 mass of the chi. So why is this different? From the point of view, the decay of the dark photon is the same, because the dark photon will, in these 2 scenarios, visible and secluded, will decay in standard model leptons, but standard model particles. But the difference is in the annihilation. So how it is achieved, the equilibrium in the early universe from the point of view of the freeze-out. In the visible case, you have this S-channel annihilation, whose cross-section depends on epsilon square and alpha dark. In this case, when the mass of a dark photon is lighter than the mass of a chi, what happens is that you can produce on-shell dark photon, so this particle here, and they can later decay to standard model particle. This means that the equilibrium in this scenario is achieved via a reaction that does not depend on epsilon square, which is the coupling, again, between the dark matter and the standard model. So while in these two cases we can say something about what is the minimum value of epsilon to be explored at the experiments in agreement with the thermal origins of dark matter, in this model here, for this ratio of masses here, we have no target for epsilon. So what this means is that if the mass of a dark photon is lower than the mass of the chi, any small value of epsilon is achievable, and this means that the dark matter and standard models can be completely decoupled, and it could be impossible to explore, to basically produce dark matter particles at accelerators. There is no target for exploration, no minimum value for this epsilon to explore. So this is a scenario that is not considered at accelerator searches, and I won't talk about this. So we will focus to these two different pictures, which are mass of a dark photon between the mass of the chi and twice the mass of the chi, and mass of a dark photon larger than the mass of the chi. So we'll have, from a phenomenological point of view, two possible situations where dark photon decays to standard model particles and dark matter particles. Okay, now we have defined a bit the model. We can think of searching it as with direct searches as we did before for the WIMPs. And this is something that has been done, and there is a lot of research in this field, as Javier will show, I think, in his next lectures. But there is this issue that is that if a dark matter mass goes below the GeV range, the recoil energy of the nucleon, if you are thinking of a classical WIMP searching strategy where you search for the impinging of a particle on a nucleon, goes down because it depends on the mass of a dark matter candidate to the square divided by the mass of the nucleon. So you have to think of something new, and in particular you may think on scattering of electrons, as Javier was discussing before. This is an ongoing effort, and it is critical that the direct searches proceed in that way, because if you want to be sure that what we see is dark matter, we have to see it with a direct search experiment. But still, this scenario, where the masses are sub the GeV range and between the 1 eV and 1 GeV, it's very well suited for the search at accelerator, as we will see in the next slide. So this is a scenario that is usually searched at accelerator experiment, and these are the parameter space that are explored by many different experiments. All the limits that are set here are limits set by accelerator experiment. So here you have the change in paradigm from the WIMPs. So from a scenario where usually the limit and the sensitivity of experiments are shown in this plot with the mass of the dark matter particle and the dark matter nucleon interaction, towards two new parameter spaces, which are one for the visible scenario, sorry, this one, and one for the invisible scenario. So depending on the ratio between the mass of a dark photon and the chi particles, you have two different phenomenology, in particular the decay of a dark photon if you produce it, and then you have two different scenarios for the experiment to explore. This black line here are the so-called thermal targets, so are that region of a parameter space that can explain the dark matter in the thermal relic hypothesis, and here are represented in red for the visible scenario. And you can see there is still a lot of space to explore to reach these curves here for experiment. In the next slides, I will show how what are the different strategies to search for dark photons and light dark matter particles in the two scenarios. Before moving to the experiment, just a little bit of phenomenology for the dark photon. So as I said, in principle, dark photon is coupled with the kinetic mixing to the standard model photon. So basically, this particle could decay via all the decay modes accessible if are mediated by a photon. So dark photon can decay in principle to leptons, hadrons, and also to particles of dark sector, obviously if this is available due to their mass and we are in the so-called invisible scenario. This is the total width of the dark photon, and this defines what is the lifetime of a dark photon. So depending on all these decay modes, which each one has its own width, the dark matter, the dark photon lifetime may vary a lot. And this is in particular true if you consider how the width, the partial width for the decay of a dark photon to standard model particles and dark matter particles are made. So here I have formulas from the decay for the width, which is not really important here, the details, but I just want to show that this one depends on epsilon squared, and this one depends on alpha dark. So dark photon is coupled to the dark matter particle via this coupling alpha dark, which it does not have to be small, as I said before, while it is coupled to the standard model via this epsilon parameter, which has to be small. So it's obvious that this width is dominant, and if it is, as we said before, it is kinematically accessible if the mass of a dark photon is larger than twice the mass of a chi, this will be the dominant decay ratio, and this will be the dominant contribution to the total dark photon width, and therefore to its lifetime. Obviously, this is true, as we said, for the invisible scenario, where the mass of the dark photon is larger than twice the mass of a chi. If you are in the visible scenario, this part is no longer there, and the dark photon can decay only to standard model particles, and therefore to a width which depends on epsilon squared. And in this case, in the visible case, where the dark photon cannot decay to dark matter particle, and where the decay width depend on parts which depends on epsilon squared, you have that the lifetime of a dark photon may vary a lot depending on the value of epsilon you are searching for. So for very small value of epsilon, you can go to very short lifetime. So basically, as long as you produce a dark photon, it decays. But if you go to the opposite direction of a parameter space, you may have very long-lived dark photon, which lives more than 100 seconds. So if you consider their velocity, even if you produce them at accelerator, they basically escape the accelerator, the detection zone. So depending on the value of the parameter, you may have very different phenomenology from the point of view of accelerator experiment. Here I have the parameter space for the visible scenario, and here the arrows defines what I was mentioning before. So these are many experiments which search for the dark photon and place the limit in these scenarios. And basically, if you go down in y, which is the coupling epsilon, the dark photon will be more and more long-lived, while if you go up, the coupling increase, the dark photon will be short-lived, and it will be easier to produce it because epsilon is bigger, so the portal between the standard model and the dark sector, dark matter is stronger, and therefore it's easier to produce it. So you see, for example, all the experiment here, this shows the explored region of this parameter space. We're able to explore it since the coupling is big, and they were able to explore this region, while these other experiments are beam dump experiments. We will discuss of that in the next day. So for today, we will stick with collider searches. We produced this kind of plots here. But more in detail later. So there are, as I said, many experiments and many strategies to search for light dark matter particles in the dark photon paradigm. You may think to use thin target experiment, so you have particle beams impinging on very thin target, and then you look at the produce of the decay of the dark photon, for example, that you produce. These are two cases. One is the PADM experiment, and one is the HPS experiment. You have beam dumps, so when you try to produce dark matter beam, basically making a lot of energy particles impinge on a thick target, and then you have a detector downstream where you hope to see the flux of dark matter impinging on this detector. You have a missing energy experiment, which I will explain in the last day of our lectures. And finally, but first, you have the collider, where you produce dark photons and dark matter particles in the impinging of two beams, colliding beams of high energy particles. For this lecture, I will stick with colliders, and in particular, I will describe a bit more in detail what is the status of the dark photon and dark matter search at the LHCb experiment at CERN. So here you have a nice picture of the detector LHCb, so you can get an idea of the scale. And I will describe you what is the experiment, technology used, and the strategy for the search for dark photon at LHCb. First of all, LHCb is located. Sure. Yes, this will be explained at the end of the talk. This is given by the fact that LHCb, to search for these particles, has used two different strategies. I will explain it as I arrive to it, but this is very interesting because it's the only experiment that used this strategy in this parameter space up to now, so it's very interesting. Okay, so I think you all know about LHC, which is the larger collider of particles in the world. It is located close to Geneva in Switzerland. It is 27 kilometers in diameter, so it's very large. It has an order of 1,000 dipole magnets, almost 15 meters long, almost 400 quadrupole magnets. And at LHC, Large Hadron Collider, you have collision between two proton beams which reach up to 13 TeV in the center of mass, so a very incredible energy. And this interaction happens into four interaction points, which are located around the LHC circumference, where the main experiments of CERN are located, which are CMS, ATLAS, ALICE, and LHB itself, LHCb itself, which is the one that I will cover. So CERN is obviously a gigantic machine which many physics goals, from investigating the origin of baryon masses, the Higgs physics. Higgs has been discovered here in 2012, but also dark matter searches, SAIP evaluation study, and supersymmetry, and so on. So LHCb is located at CERN, and it is a single-arm forward spectrometer which covers the pseudo-rapidity range between 2 and 5. So pseudo-rapidity here is just a fancy way to define the angular acceptance of a detector. So here you have the beam. The two beams, one comes from the left, one comes from the right, and they interact in this point here, basically. And then you have a lot of detectors which are placed in a precise order to try to detect all the different particles, and the idea is to study in particular the production of particle contains boson and charm quark. So really, the dark photon searches is not the main goal of LHCb, but still the experiment, given its outstanding performance, has really an important sensitivity to these models. I will go a bit more in detail on the detector and the different parts of the detector, since I think it's interesting from the point of view of collider in general. So what is the goal of a collider? Basically, you want to detect all the particles resulting from a collision, of, in this case, from two protons. And to do so, you want to measure their momentum, the angle of emission, but also understand the type of particles that are produced. So you need many different detectors to do so. And the first one, which I are going to discuss, is the tracking system. So the system which is responsible to measure the momenta of the produced particle. And this is done through a system of three main detectors, and a magnet. So the first one is a vertex locator, which is called VELO, which is placed just around the interaction point. So here these are silicon strips that you can imagine as the CCD of your phone camera. So basically, these are pixels, and when a charged particle passes through the pixel, it will register a hit, and you can reconstruct where the particle passed. You have many of them. So using the information of all of them, you can build the trajectory of the particles. You have, as I said, the first one is close to the interaction point. Then you have another just here. And then you have a magnet. The magnet bends the track of the particle. The bending depends on the moment of the particles. And if you measure again with other tracking stations the impinging position of the particles after the magnet, you can build their momenta. So this is a system, basically, that measures the momenta and the angles of emission of the particles. Why it is put, put close to the interaction point? Because you want to do this to measure the emission of the particle, their momenta, before they are degraded in the energy by other part of the experiment. So to say the calorimeter here, which I will discuss later. So this is the system of tracking for FCMS. We have more details here. And it has a really outstanding performance because it can reach a resolution of order 1% at 200 GeV, and also can measure an impact parameter, which is basically the distance of the emission of the particles with respect to the primary vertex where the two particles impinged, with a really outstanding precision. Okay, so after you have measured the momenta of the particles, you end up with a series of particles with defined momenta, but still you don't know which particles have been produced. So you need some detector to distinguish between the different particles produced. In particular, you produce many hadrons in these collisions, and you want to know what have produced. And this is done through two different Cherenkov detectors. So one is called RICH1 and one is called RICH2. RICH stands for ring imaging Cherenkov detectors. And the idea is this. You have particles that are produced in the interaction vertex that cross a region where some gas with well-defined refraction index is placed, and then particles produce Cherenkov light, as it was told this morning at the previous lessons, depending on the refraction index of the material, but their velocity, which at fixed momenta depend obviously by their masses. So you have the light emitted that is reflected through mirrors to photodetectors, which detect this light, and detecting the angle of emission of the light via this Cherenkov reaction, you can basically measure the velocity of a particle and, knowing the momentum, know the mass of the particle, or at least distinguish between the different particles. Why they are two? They are two because you need to cover all the angular acceptance, and when you are very close to the interaction point, it's not accessible, you cannot access the very close part of the beam due to radiation, so you lose the sensitivity to the low impact angle, the low azimuthal angle region. So this first reach as a sensitivity, as an acceptance for the larger angles, which are from 15 to 120 millirads. And then you have a second one which can achieve, due to the distance to the interaction point, can achieve an acceptance to lower angles. Here you have, for example, how a typical event is represented in the Cherenkov rich one Cherenkov detector of LHCb. So what happens is that every particle that passes through the Cherenkov will produce photons through Cherenkov light. These photons are conveyed and focused by mirrors on the photon detectors. And what you see in the photodetector are these disks which represents the emission of the Cherenkov light throughout the trajectory of the particle within the Cherenkov detector. The diameter of these disks basically allows you to reconstruct the velocity of the particle, and in particular the diameter of this disk depends on the Cherenkov angle, so the angle of emission of the light, and therefore you can build you can evaluate the velocity of the particle. So you can see here there are many, this is a single event, and there are really many particles passing through the Cherenkov detectors, so you really need some sophisticated algorithm to distinguish between different disks and associate to each disk a particle, so really sophisticated analysis. Here you have the distribution of this Cherenkov angle for different particles crossing the Cherenkov detector at different momentum energy. And as you can see that if you consider energy before 20 GeV, you can easily distinguish between kaon pions, but when you go up in energy, all the particles tend to behave the same in the Cherenkov detector. So basically you have some resolution in the particle identification up to some energy, and this helps in the definition of the different particles and the physical analysis of LHCb. So the last part I'm going to talk about is the calorimeter system. So after the particles that pass through the tracking systems, the two reaches, they reach the calorimeters where they are finally degraded, is to say their total energy is measured. These are high energy particles, so they undergo many interactions. If they are electrons, they produce showers. If they are hadrons, they produce hadronic showers. So the important thing here is that you need some large volume to stop this particle and to measure their energy. The technology here is scintillator. So for all the system composing the LHCb calorimeter system, which is divided in 4 subdetectors, you have the same technology, which is plastic scintillator, organic scintillator, which means that you have, when a charged particle passes through, you produce light. And this scintillator is interleaved with absorbing plates of iron or lead to make the detector more compact and allow to contain the particles and the electromagnetic shower and hadronic shower produced in the detector. Here you have some pictures of the elements which compose the calorimeter. Yes. So this is due to the main physics goal of, I mean, in principle, if money were not a problem, you would desire a detector which is 4 pi, so covers everything in all directions. but this is not always possible, and these are very expensive experiments already like this, so you have to choose. And for the kind of physics that LHCb was think of, which is B and C quark studies, this is the pseudo-rapidity values of interests, so between 2 and 5. So this is the angular acceptance, which is interesting for the detector. So this has nothing to do with dark photon searches. It's something that really was thought of when the experiment was designed for its original purpose. Okay, so calorimeter, yeah, so these are the pictures of the elements composing the calorimeters. So this is a cell of what composes the first layer of this calorimeter, which is made by this matrix of plastic scintillator, which is a material, as we said, that emits light when a particle crosses it, and the light emitted depends on the energy deposited in the material. And then you have some fibers, you can see them inside, that collect this light and bring the light to photodetectors, which may be phototubes, in this case are phototubes. And for the other parts of the calorimeter system, the strategy is basically the same. Just the arrangement of the plastic pads differs from the different subsystems due to the kind of electromagnetic or hadronic showers that you want to detect, so the containment you want to realize, and so on. So this is the technology for this experiment, for this part of the detector. Okay. So another interesting aspect of this kind of detectors and of experiment in general is the incredibly large amount of data they produced and the relevance that the triggers has to the sensitivity of the experiment itself. So when you work in nominal conditions in LHCb C, you have a rate of interaction which is of order of 40 megahertz, okay? And you're talking of a typical event dimension, if you want to save every information from every part of the detector, of order of 200 kilobytes. So you can make a calculation and we easily understand it is impossible to save everything, okay? You have somehow to decide what to save on disk, and you have to decide it quickly because you have to do it basically on the fly. As soon as you acquire data, you acquire an event, you decide if it's a good, interesting for you event or not, and if it is, you save it, if it is not, you don't save it. So to do so, to reduce this very large rate of 40 megahertz of events, this experiment has a very convoluted, complicated system of trigger, that is to say a system of conditions on different levels on what are the characteristics of an event to be good to be saved. So there is a very low level, which includes only information for calorimeters and the muon system, which is called level 0. And you do some preliminary decisions. So if some conditions are not satisfied, you simply don't save any events. And there is more sophisticated software conditions, which are called HLT1, HLT2, which are done on a software level. So you have to basically save preliminary the event that you selected level 0, perform some preliminary analysis on these events where you already build some of the physical characteristic of the particle produced in this event, and then use this information to reject or save these events. So as you can see, this is really complicated and requires a lot of computing power, but without going into further details, it allows to reduce a 40 megahertz rate to 12 kilohertz rate of events saved. So allows to save only events that are interesting for the physics of the experiment and reject all those events where nothing important happened from the point of view of physics search of the experiment. Okay, we finally come to the dark photon search at LHCb. So what is done in LHCb to search for dark photon? The idea here is to produce the dark photon via different processes. We have in particular the decay of mesons and Drell-Yan processes. Decay of meson is more dominant for energy masses of the dark photon below 1 GeV, while Drell-Yan is important for masses larger than 1 GeV. The difference is that in the meson you have the interaction between the two protons of the beam, which give rise to the production of a very short-lived meson, which decays to dark photon, which then decays to muon pair. And the Drell-Yan, instead, is a process that happens at a quark level. So basically, from our, for the sake of our discussion, you have two protons impinging, and you have the dark photon exiting with some other standard model stuff. So in both cases, we are interested to the decay of the dark photon to two muons. The reason for this is that muon particles, which are really penetrating, cross easily all the layers of the detector. No, sorry, I want to go back. Okay. It stopped working, okay. Okay. I was saying muons are not stopped, for example, in the calorimeter because are ionizing particles throughout much of their energy range. So what they do is cross all the detectors and arrive up to the last part, which is a part dedicated explicitly to the detection of muons. So it's very easy to distinguish a track of muon from all other particles. So two muon in an event is a really clear signature for this kind of experiment, and you can basically reject most of the other backgrounds, and it's really a good signature to search from rare events, which is the case for dark photon. So an important aspect of this search at LHCb is that given the nature of a dark photon and the fact that it is coupled to standard model photons, basically the decay products of a dark photon inherits all the properties of the standard model decays, where you produce simply a pair of muons via a standard model normal off-shell photon. This is the star for off-shell. So usually in an experiment such as this I'm describing here, where you are searching for something unknown, you need to know what is the efficiency of detection for your experiment to this kind of signature, let's say 2 muons. Because if you want to explore, to put limits on a theory, you basically have to know the efficiency of your experiment to this signature. This is not easy to do. You have to do, in particular, if you have a signature from dark matter particles, which you don't know. You have to rely on simulation to other studies that results in a large statistical systematic uncertainties. In this case, this is bypassed because kinematically, the decay of a dark photon to 2 muons is basically the same to that of a normal photons, of a production of a pair of muons through a standard model process mediated by a normal photon. So the result is that you can normalize the number of expected events of dark photon, or let's say of muons decay from dark photons, to the number of observed events of muons from standard model processes which are bound by this equation here, where epsilon is the coupling constant of the model. Here you have this term here, which includes some phase space parameter, which depends on A prime, but they are known and can be calculated. And here is the efficiency ratio between the dark photon, the detection efficiency between the detection of dark photon decaying to 2 muons and 2 muons produced by standard model processes. But this, as I said, since the process basically are the same from the point of view of kinematics, from the point of view of the detector, this is 1, because the efficiency of detection of 2 muons produced by a dark photon or produced by other processes for the detector is the same. So basically, you can exploit this reaction to normalize your search to an observed quantity, and therefore you don't have to include in your analysis systematic effect which could affect your sensitivity due to the fact that you don't know perfectly the performance of a detector. So this is really a data-driven search. So now, before moving on, I finally come to the question: what was difference was spot in the parameter space? This is due to the fact that LHCb searched for 2 different signatures of this dark photon, which is to say displaced vertex and prompt vertex. So for some region of the parameter space, you have a dark photon which is long-lived enough to produce a displaced vertex which is accessible to the resolution of a detector, and for others, no. So they split the sample into 2 different data samples and performed 2 different analyses. So this is the spectra for the prompt muon decay, so the decay where the dark photon is basically very short-lived, so you don't see any displaced vertex. Indeed, you can see what is the reconstructing missing mass for the dimuon events after the selection. You see that there are many resonances due to the production of standard model resonances, and here is the distribution that was used to search for this dark photon events. There are several backgrounds which are shown here in blue, and these backgrounds are mainly due to the fact that you can misidentify particles for muons. So you think you saw a muon reaching up to the muon chamber, but instead was an hadron, in particular maybe a pion, that is not stopped inside the calorimeters, and it is reconstructed as a muon. Or maybe you may have muons which are produced in other processes which are not the decay of a dark photon, but are produced by the decay of hadron containing heavy flavor quarks, and so on. So what is done is to consider this background and include them in a very complicated fit procedure that includes all, as I said, the backgrounds, the shape of the signal. Each part of this spectrum here was fitted to search for dark photon, and this is the limits that are placed in the dark photon parameter space. That is to say, the parameter epsilon resulting from the fit is basically compatible with 0 through all the scanned mass range, and this shape reflects the fact that since you performed many fits and different invariant mass bins, basically, statistically there's some oscillation due to the statistical fluctuation of the backgrounds and so on. So this is the result. These holes here in the sensitivity are the holes, due to the fact that in that region, basically you have the standard model resonances. So you have mesons which are produced in the collisions, that decays to muons and basically produce these peaks, which makes it impossible to disentangle muons produced from dark photons decay to muons produced for standard model mesons in this mass range. So this has been completely cut from the analysis. No, this is not the case. So, I mean, this is, for example, you can see all these peaks. You have many particles in the standard model, which are mesons, which can be produced in the collision of proton and proton, and they are very short-lived, so they decay promptly. So basically, you don't see them, you just see the decay products. In particular, they can decay into muons, and close to their mass, okay, so invariant mass close to the mass of these particles, the cross-section of the production of these particles is very large. So what happens is that you have many of these events in this region, which makes it impossible to perform the analysis. And hence, what they decided to do is to cut this part from the invariant mass spectrum of the muons, and to not perform the search in this region. So this is the case. So this is the resulting exclusion limit. I was a bit slow, so I think for tomorrow I will show the analysis of the displaced vertex of LHCb.
So unfortunately, we're running a bit late, and otherwise you won't have time for lunch. So I suggest you ask questions offline. But we are thinking a way to have more time for interaction, so we'll communicate this later. So let's thank again Luca. I have some few